Well, thank you all for joining us for this. I was given a very fixed amount of time, and hopefully I won't run over. As I always tell everybody, it's not hard to get me to talk about sloths. It's hard to get me to shut up. So let's get going on it now. And just the way of a little bit of background, obviously there's more than what we can do in this time that we've got allotted. So I've picked a few interesting tidbits to sort of give an overview on fossil sloths and try and put perspective in some interesting sites we've gotten our information from and some of the history that goes along with our learning about ground sloths. And of course, for most of you, this is totally redundant. We all know what the order Xenarthra is. And of course, for a lot of people, I have to translate this as strange joint and point out this does not refer to what happens here in Colorado, since they passed a certain law allowing strange joints to be available. And of course, you're all familiar with the modern three main subdivisions of the Xenarthra. Most of you have worked with one or more of these. But when we get into the fossil record, we get a lot of interesting animals that unfortunately are no longer around, but available to us through the fossil record. We've got our glyptodonts, the pamphotheres, which are really giant armadillos, much bigger than priodontes, and then, of course, today's topic, the ground sloths. And in recent years, we've really had a lot of changes in our thinking about relationships, but we've also had a lot of reinforcement of what morphology's told us. And this is a relationships based on DNA that's been worked out, showing based on the molecular clocks when the various groups split off. And of course, up here in the Paleocene, we get the sloths and the anteaters separating off. And of course, as illustrated by our two living genera of sloths. And these are the ones that most people are familiar with, the three-toed sloth and the two-toed sloth. And of course, I can't talk about them because they don't have a fossil record. One of the biggest interesting gaps we have with fossil sloths is simply the fact that neither of the living genera has yet been recovered in any fossil context. So to me, that's one of the holy grails that we have with regards to learning more about the relationships of sloths, is eventually being able to plug in, based on the fossil record, either of these genera or hopefully both at some time. So what I'm going to be focusing on primarily, you can take for fossil sloths as belonging into four different families here: the Megatheriidae, the Nothrotheriidae, the Mylodonts, and the Megalonychidae. So those are going to be the four major groups I'm going to be providing examples of and talking about with regards to some of the interesting aspects we know about the fossil record of sloths. And you can see here, one of the more recent studies that's been done, all of the taxa listed here are basically genera of fossil sloths. So you can see that once we get into the fossil record, there is a phenomenal diversity of sloths out there. And if you look at the top, you can see the Megatheriidae, the Megatheriidae I mentioned, and they split off closely related to the Nothrotheriidae. And then we get to the Megalonychidae, and at the bottom, the Mylodonts. And it'll give you an idea of sort of the diversity and some of the radiations that have taken place through time. And new taxa are still being discovered, being described. These are based on specimens that are fairly complete, so we've got a good suite of characters to determine relationships. There's a lot of fossil sloths out there that are still only known from the type specimens, often single bones or fragments of jaw, not a whole lot to work with. So while this sort of looks like a phenomenal diversity, it's only really a small part of the total diversity that has been formally described in the literature with regards to fossil sloths. Well, if we're going to talk about fossil sloths, we have to go back to the father of comparative anatomy and vertebrate paleontology, Cuvier, since he is the one that described the first fossil sloth, and he's the one that coined the name Megatherium americanum. And here's an early illustration. And Cuvier has the dubious distinction that he created this new fossil sloth, or recognized it, without ever seeing the original bones or skeleton. He actually was sent drawings, or surreptitiously, of this beast that was found in Argentina, in the province of Buenos Aires. And it was from these drawings that he actually figured out that this extinct animal was a fossil sloth. And that skeleton is still there today in the Natural History Museum in Madrid. Originally, when it was collected, it went to the king's cabinet, was presented to the King of Spain, and one of his people that took care of his cabinet was in the process of getting the drawings made, planning on describing this animal before he got usurped at doing it by Cuvier. And so we have Megatherium, the great beast of the Americas. I might also point out that this sloth, besides being the first one described, was the first fossil vertebrate for which a Linnaean binomial name was given, the Megatherium americanum. And it's also the first fossil skeleton that was mounted three-dimensionally on iron supports as a museum exhibit. So when we're talking about the history of sloths, not only do we study it, think about their evolution, their paleoecology, but how they fit into contributing to our understanding the world through museum exhibits and broadening the scope of Linnaean taxonomy. So sloths may be slow, but they've been the first at a number of different things. And that. Well, one of the key features that Cuvier picked up on from the drawing was the presence of this bony flange below the eye in the skull of Megatherium, and recognizing that he had seen that in the skeleton of the modern sloths. And so that bony flange there, to which the masseter muscle attaches, is one of those very distinctive features that you see in sloths. When we do a session on glyptodonts, we'll be talking about that also, but the way it forms and the way the muscles attach in glyptodonts is quite different than what you see in sloths. So how this is designed to move the jaws for processing food is quite different in both of these groups. And of course, other distinctive features of the sloth is the teeth have no enamel. Of course, that's also true of Xenarthrans in general, as most of you know. They have no deciduous teeth, so they get one set of teeth here that are ever-growing, and you can see the way they intersect here. They're self-sharpening. So you get one set of teeth. They grow throughout the life of the animal. And if you look at some specimens that have been collected from tar pits, they actually found twigs in the mouth preserved. And if you look at the length of these twigs, they're all about the same length and match very nicely the distance between the cutting edges of those self-sharpening teeth. So these are some of the many interesting and consistent features that we see in sloths, is this lack of deciduous teeth, no enamel on the teeth, only made of osteodentine of different types that have slightly different hardnesses, so they wear differently, and you get these self-sharpening teeth. One of the nice things is that we can actually take these teeth that are ever-growing, so the rate of growth compensates for the wear of the teeth while they're chewing their food, and much like what's been done with mammoth and mastodon tusks, where you can look at the history of the animal by the length of the tooth and measure throughout the tooth oxygen isotopes that are sampled, or strontium isotopes to tell us about the landscape they're on, carbon and nitrogen isotopes to tell us about the diet, so we can get a little bit of the paleoecology from a single tooth over about 1.5 years. Right now, it looks like the tallest tooth here, and by all this sampling, tells us that there was a wet season, a dry season, and another wet season. So we've got just about a year in the life of this particular sloth that's been sampled from these ever-growing teeth. So a lot of the new work that we're learning about the paleoecology of sloths is coming from looking at stable isotopes and giving us ideas of their diets and climatic variables that are going on during the life of the animal. Well, we're going to start out with the Megatheriidae. And of course, the best known is Megatherium, which is found primarily and only in South America. And it seems to be found in the more temperate regions of the continent, and it gets up into the Andes. So when you think of high elevations, the Altiplano and the Andes, the fact that we find sloths there immediately tells us that it's quite different for many of our fossil sloths with regards to their ecology and climatic preference, in contrast to the two living sloths, which are both confined to the tropics. But that doesn't mean we don't also have extinct tropical ground sloths as well. And this one on the left here is Armadillo, a close relative of Megatherium. And one of the things that's very interesting is it's found strictly in tropical and subtropical regions, and it's actually bigger than Megatherium. So Armadillo is the largest in body size, followed by Megatherium of all the extinct sloths. And a lot of research has been done because Armadillo shows up in a lot of locations over a very wide range, and it actually got into the United States, where we finally find it mostly along the Gulf Coast, but one specimen got all the way up to New Jersey. I don't know if this one had a penchant for gambling and was heading up there for the casinos, but we do think that it was probably there during an interglacial period, and that for most of the record of Armadillo, it's in the Gulf Coast in Florida. But if you look here, you'll see the record goes down through Mexico, Central America, into northern South America with a couple of records in Peru and Ecuador, and then down through the tropics to southern Brazil, with maybe one just getting into northern Uruguay. This is the widest distribution, the widest range of latitudes that any sloth is found at. So it's often referred to as the Pan-American sloth. The first specimen was found in Brazil, but as you can see, being a large animal, it's easily spotted, often found, and has a phenomenal fossil record based on literally hundreds of localities. If we look at some of the interesting sites that we have for the Megatheriidae sloths, we're going to go to Argentina, to an area called Bahia Blanca, at a locality called Cuenco. And it's a famous ichthyological site. And I want you to note that at this point in time, the site is right on the coast. In fact, you can only go out and visit the site at low tide, so you have to have a tide table to know when you can go out to see the site, because part of the time it's covered by water. But during the Pleistocene, this deposit was an inland lake. And so you have the coastline here during the glacial maximum, the glaciers building up in the north, the drop in sea level exposing this coastal plain. And so Bahia Blanca at one time was well inland and not on the coast as it is today. And as I said, this is famous for its tracks. And just to give you an idea of the size of Megatherium, which would have been the genus that's there, this is its track. At the top here, we can see where the claw left its impression. We can sort of see the scaly pattern of the soles of the foot. And as he was walking through the mud, you can see how they would push mud up on the side here. And this is a trackway of a Megatheriidae. You'll notice that the hind foot shows up very well, but there's not much to show you where the front foot is. And the contact of the front foot is much smaller with the ground than the hind foot. And as they're walking around, the hind foot comes down on top of the front track and obliterates it. And the only time you ever see the front track is when the animal is changing directions and there's sort of a overstep. And of course, this has led some people to interpret that the Megatheriidae were walking around bipedally. I think that it's mostly can be explained by this overprinting, but it certainly gives you an idea of some of the ways that we can calculate the speed these animals were walking by measuring the distance between these tracks, applying some formulas that were used for dinosaurs to calculate the speed, and they're moving along at a fairly leisurely rate of, maybe a half a mile an hour at the most. Well, we could spend all time talking about the different megatheriidae and that, but I'm going to move on to some more history here with the discovery of these bones in a cave in West Virginia in the United States. People were mining saltpeter that was used to make gunpowder, and the bones were uncovered. And it led us to suppose that some large clawed animal was living in North America. And these bones were sent to our third president of the United States, Thomas Jefferson. So he had an interest in fossils and in paleontology. And so the first discovery of a sloth in the United States, the second sloth to ever be described, was named Megalonychidae after the large size of its claws here. Now, what happens is Jefferson gets a lot of the credit for writing the general paper about this new beast, but there's a second paper that was written by Caspar Wistar, one of the leading doctors and anatomists in the late 1700s, early 1800s, and he's actually the one that did the anatomical description of the bones to complement Jefferson's paper about the discovery. And while these illustrations here are often misrepresented as being part of Jefferson's paper, they were actually part of Wistar's paper. So if you want to learn about the first description of Megalonychidae, you need to read both papers, both Jefferson, who got the credit, because later, although he coined the genus Megalonyx, he didn't give it a species name. So he wasn't quite as conscientious as Cuvier was in making it a true Linnaean binomial. But later, the species name jeffersoni was added in order to acknowledge his contribution. So this is the beginning of the family Megalonychidae, taken from Megalonyx jeffersoni. Now, if we look at the Megalonychid ground sloths, what distinguishes the family is that the very first tooth here is secondarily modified into a caniniform, and then the cheek teeth that are doing the chewing are often referred to as molariforms. We don't actually know the true homology between the sloth teeth and that of other placental mammals. And here you can see the lower tooth in Megalonyx, which is modified to be sort of tusk-like for grabbing vegetation, and the very simple teeth here in the molariform teeth. And what we have to keep in mind is there's been a phenomenal modification in sloths in that they only have a maximum of 5 upper teeth and 4 in the lower jaw. And so trying to come up with the homologies of which ones are, is this caniniform really a canine? Probably not, hence using the term caniniform, while the cheek teeth here are molar-like, so that we just call them molariforms, but we don't want to suggest that we've actually figured out how these teeth compare with other placental mammals. But we can definitely say that there are no incisors either in the jaw or in the skull, so these have to be possibly a canine, maybe premolars and molars. That's still something that needs to be worked out. Hopefully, in some of the earliest records of sloths we'll find far enough back where we can actually get some with maybe more than 5/4 teeth, but that's not the case today in terms of our knowledge of the fossil record. Here's just another shot of the skeleton of Megalonyx. This is based on a specimen that came from a bog in Ohio. And so when we're looking at studying sloths, we actually get many, many different types of depositional environments. We find them in caves quite commonly. We find them in peat bogs. They are found in normal sedimentary deposits. We've even recovered them from cenotes and spring deposits. So sloths are certainly found in many, many different types of environments. In the North America, we can see Megalonyx is extremely widespread. It's known from coast to coast. And you'll notice there's even some northern records here, getting all the way up to the Yukon. These northern records are during the last glaciation. So as I mentioned before, with the Rematherium getting out of the southeast during the last glaciation and getting up to New Jersey, Megalonyx went even further. It's been found in Alaska, the Yukon, up here, and other sites in northern Canada, and of course, very widespread. It is the most common of the North American sloths. And for many years, it was the only late Pleistocene Megalonychid that we had. But recent work in the cenotes and flooded cave systems, caves that were dry during the glacial maximum when the water level of the oceans dropped 100 meters, and these caves in this limestone platform on the Yucatan Peninsula were dry caves. There was no surface water, but there was water underground. It was also attracting animals to the water supplies, and we've recently been finding Megalonychid sloths, equal in size to Megalonyx, down in southern Mexico and in the cenotes and cave systems there. But they're quite different in their anatomy. They're different genera. This is one that was described. Megalonyx, as I mentioned before, means great claw, as coined by Jefferson. And we decided that since this was also a Megalonychid sloth, it was also a great claw, but in this time we would use Mayan. So Noho Chichak is basically great claw in Mayan. So we kind of took a shortcut in coming up with its scientific name there. Xibalba is the underworld that the Mayans were feared, and Aka means dweller. So in the peninsula of the Yucatan, we have the great claws that dwelled in the underworld. So we are learning a lot more about sloths in the tropics. Basically, all of our knowledge of megalonychids in the past has come from temperate North America, and now getting into southern Mexico and down into Central America, we're making a lot of new discoveries of sloths that were living in the tropics. So once again, we've only really scratched the surface. There's many areas yet that have not been fully explored, and new discoveries are being made all the time. And that also includes the Caribbean. So it just so happens, if you're interested in megalonychid sloths and want to study them, it gives you an excuse to go to Cuba, Hispaniola, Puerto Rico, the Netherlands Antilles, where we have them on Curacao, and they've even been found on the island of Grenada. And we recognize that these sloths dispersed into the Caribbean millions of years ago, long before the islands were in their present conformation. The moving around of the plate tectonics of the Caribbean plate and the South American and Central American plates have made it much more difficult to sort of figure out how they got there. So we don't know if there was a land barrier. It's been suggested that they came up to the Lesser Antilles, or if these islands were more closely related together, but still they had to cross a water barrier. And of course, at this time, the Isthmus of Panama did not exist, and there was a water barrier between South America and getting into North America. So Megalonychid sloths were phenomenally good dispersers, better than any of the other families. And if we look at the variety of sloths that you find, we recognize 4 genera: Megalochnus, Acrotochnus, Parochnus, and Neochnus, and multiple species. And of course, we often think of sloths as being the megafauna on the continents in America. Obviously, if you get sloths the size of Armadillo and Megatheriidae that are elephant-sized, they definitely qualify as megafauna. And if you go into the Caribbean islands, sloths are once again the megafauna. They are the largest herbivores that you find in the late Pleistocene, but Megalochnus was still only the size of a North American black bear. So being a megafauna is relative depending on where you are and whether other animals are around. But once again, they all have this characteristic enlarged caniniform in front of the skull. And then we have Paleochnus, which is the one found on Curacao. So who knows, maybe more work in the Caribbean on some of the other islands may turn up sloths, but they've already got a pretty good distribution. And once again, in Hispaniola, especially in the Dominican Republic, we find lots of the sloth remains in caves. And recently, once again, when sea level was lower, some caves were open and available. Later, they got submerged, the sea level came up. We've got people doing cave diving in the Caribbean also recovering sloth remains, just like they've been doing in the Yucatan. The next family that I'm going to be introducing you to are the Mylodonts. And now we start getting something very different. We think of the Megatheriidae as browsers. We think of the diet of Megalonychid sloths as browsers. But when we get into the Mylodonts, we start getting into sloths that look like they're more grazers. They're feeding on a very different type of vegetation. And if we look at the Mylodontines on this side here, and we look at the skull, we notice there tends to be a flaring here. And their teeth, rather than locking together and with cutting edges like I showed you in the Armadillos, and which is present to a lesser degree in the Megalonychids, the teeth are flatter. They're more for crushing and grinding the vegetation, which is where they get the name Milo, meaning mill or grinder tooth. And so this is a very different type of tooth than what we see in the other sloths. They're lobate, so they're a little bit more complex in their outline. But the other subfamily is the Scelidotheriidae. Some people want to make them 2 different families, 2 different subfamilies. They're obviously sister groups and closer related. So at what level you want to split them off is just a matter of your version of taxonomy and how you set up your classifications. But unlike the Mylodonts here with this flaring snout, in the Scelidotheriidae, they've got this long, narrow muzzle and spout on the lower jaw. So what we're thinking of is the difference between the two is here you've got sort of more of a diverse feeding anatomy. It's feeding on lots of different vegetation and not too selective in terms of what parts of the plants it harvests. Whereas in these guys, maybe they're selecting more specific parts of the plants, so they're more selective feeders. But in both of these animals, you'll notice the bones are very short, very robust, and their claws seem to be also well designed, not for hooking and grabbing branches, which, like we see in modern sloths, was probably also the case in the Megatheriidae or in the Megalonychids, but that they may have done some digging. And there's been some cave systems or tubes found in Brazil with claw marks on the side that seem to match up with the claws of these type of sloths. and there's sites in the in Buenos Aires province where there seems to be in the soft sediments caves that were dug out by these animals. So they do seem to have been semi-burrowers and maybe creating some type of small shelters, either as birthing dens or maybe as an area where they could go to get out of the hot sun if they're temperature sensitive. We're still needing to learn about them. In North America, we have a sloth, a Mylodon sloth, which is very common, which we call Paramylodon. You can see they're short, they're stout, very robust in their build. And Paramylodon harlani is the species, named after Richard Harlan, an early naturalist in North America. And Harlan described a lower jaw from Big Bone Lick in Kentucky, which is an area with salt licks. And once again, if you look at this jaw, it's got the lobate teeth that is characteristic of the family of the Mylodonts. But in the early 1800s, when he found this, only one sloth was previously known in North America, and that was Megalonyx. So he made the assumption that perhaps he had found the jaw of Megalonyx. So it just so happened that about a year before, Sir Richard Owen had published a monograph on the fossils from the voyage of the Beagle, specimens collected by Charles Darwin. And in it, he described a lower jaw as Mylodon molar tooth darwini. And once again, you can see the lobate teeth there. And Owen immediately realized that Harlan's lower jaw was not a megalonychid, but closely related to his Mylodon darwini. And so it was eventually renamed Mylodon harlani to Paramylodon. We recognized that Paramylodon and Mylodon were two distinct genera in the same family, closely related, but quite different in a number of ways. One of the interesting sites that we have here in North America is in a prison in the state of Nevada. And as the prisoners were breaking rocks, sort of the stereotype of hard labor, they got down to a layer where they started finding these strange impressions. And this was a map that was made of the floor of that prison. And there were these strange tracks, and there were mammoth tracks and horse tracks and deer tracks, quite a variety of animals. And just like the site I pointed out in Argentina, that was a lake deposit, tracks were laid down near the shoreline of a lake during the Ice Age when Nevada was wetter. And what's interesting is that you find these tracks that sort of look kidney-shaped of one size, and next to it, a smaller set of similar tracks. And these are the footprints of the Mylodont ground sloths. And it looks like what we have evidence here of social behavior is presumably a female with a juvenile walking next to it. So once again, we can use these tracks to determine something about the locomotion and the social behavior of this particular group of sloths. But once again, if you look at it, you see the large kidney shape of what's the hindfoot impression, but none of the forefoot. And so once again, these were thought originally to be tracks of a giant human wearing moccasins. That goes back to passages in the Bible that there were giants in those days. But we now recognize that these tracks are from a Mylodont sloth. For many years, these were the only ones in North America known, but recently at White Sands, New Mexico, where the wind is blowing away the loose gypsum sand, you actually can get three-dimensional impressions of trackways of Paramylodon again. So this is a new site, And what's also interesting is in this particular spot, we're also getting exposed human tracks that have been dated, and it's been suggested with the overlapping of human tracks and sloth tracks that we may actually have direct evidence of humans going after and hunting sloths based on this site in White Sands. So once again, you never know what's going to show up. We're always adding, not only from new skeletal finds, but from these track sites as well, new ways of interpreting the behavior and the predators of the sloths. Well, why do sloth hindfoot tracks look so funny? That's because these animals are actually walking on the side of their foot. So here is the fifth metatarsal, and that's supporting the animal along with the elongated calcaneum, and the foot is actually rotated on its side. This is the ankle bone or the astragalus there, and what's very characteristic is it has developed and modified the medial trochlea into this process that acts as a pivot so that the foot is actually, rather than pushing off like this, is pushing off in a pivoting motion like that. And what's very interesting is you not only find this feet modification of the hind foot in the Mylodont sloths, it also occurs in the Megatheriidae sloths. It also shows up in Scelidotheres, but you can see rather than having an elongated calcaneum here that would be flat with the ground, the calcaneum forms an arch with the fifth metatarsal, and there would have been a fleshy pad there supporting it. And in the next group of sloths that I'm going to talk about, we have the Nothrotheriidae here, which also have that rotated foot. So this is not a common feature that's ancestral. This has been independently evolved in 4 different groups of sloths. And just to show you how different some of these sloths are, here's our North American Paramylodon. Here is Mylodon darwini. And one of the different characteristics you can see is the forming of this arch in the nasal here, but they still have the flat crushing teeth here. And of course, that distinctive flange for the masseter muscles to attach there for chewing. And Mylodon darwini is the southernmost sloth. What we know, it comes from Tierra del Fuego in the south of Chile at a cave called Cueva del Mylodon. And it's a very dry cave. You actually get claw material preserved. You get the dung of the sloth here. So here's where we're getting direct information on its diet. And I'd said before that these animals appeared to be grazers. And here we have in the dung grasses and sedges that shows that this is true, that those flat crushing teeth were being used to harvest grasses and sedges, and that these are grazing animals. We also get the skin preserved. And so here we have skin of Mylodon darwini. So we have the hair on it. This is the outer view. If you were inside a sloth looking out, all these little white things are bony nodules. It's a dermal armor. You can see them in cross section here in the skin. And so this, within the Mylodont sloths, we have a number of different genera, Paramylodon, Mylodon, Glossotherium, which have this. But these ossicles are not present in any of the other families. So it's a unique feature that we see in the Mylodont sloths. And some recent research has looked at the orientation of the hair and the position of the ossicles, and has done this reconstruction showing how and what part of the body one of these pieces of skin might have fit on Mylodon darwini. And you'll notice that most of the ossicles tend to be on the back. As you go towards the belly, they tend to thin out. To the last family of sloths, we have the Nothrotheriidae. This is Nothrotheriops. It's the North American one. Once again, very common in caves. And just like in Mylodon darwini, you go back in there, all these rounded objects are coprolites. And so we've got a phenomenal amount of data. We have at least 12 cave sites in North America where dung has been recovered in Nothrotheriidae. And we've gotten ancient DNA. This is one of the first sloths that we got ancient DNA out of the dung there. And we've got identified well over 70 species of plants based on macrobotanical studies. So we have a wealth of information. And if we look at the Nothrotheriidae skull, it doesn't have a caniniform. It only has 4 upper teeth and 3 lower teeth. So it's distinguished from the other sloths like Megalonychidae and the Megalonychidae by the lack of a front caniniform. Here is a partially mummified specimen of Nothrotheriidae with patches of skin, dried ligaments, and also from these dry caves, we get its claws with the nail material preserved. And you can see exactly this claw here, which is from the 3rd digit of the foot, just how much nail material grows out past the bony core there. And to show how they walked on the back of their claws, we've actually got this articulated claw, second phalanx and proximal phalanx in its natural position, showing that it was walking around basically on the back of its claws, similar to what we see in giant anteaters. I know I'm running over, I apologize, but we are going to get to something that I suspect I'll be asked about. So we go back to South America and to the southern part of Peru and to the Pisco Formation, which is along the coast in southern Peru. This is a Miocene to Pliocene formation, and this is what it looks like. That's the Pacific Ocean in the background. And as you can see, it's very dry and it's very arid. And basically, what these mountains here are granitic hills that have been covered with marine sand. And based on the blowing wind, you just go out, you can find whales exposed. You don't have to do a whole lot of initial digging. And that variety of sharks, penguins, sea lions, porpoises. There is a lot of these marine animals are found as complete skeletons, baleen whales. So this is a very typical marine fauna until someone comes along, and here we have also showing up as complete skeletons, a sloth, which turns out to be our interpretation, an aquatic sloth that was named Thalassocnus. And you can see it's got the typical sloth morphology, and it's in with the Nothrotheriidae. 4 upper teeth, 3 lower teeth, nice flange on the zygomatic arch there for the masseter muscles. And we actually have a fantastic evolutionary lineage from the oldest to the youngest. This is about 5 million years of evolution as this goes from being a semi-aquatic to more aquatic in its habits. And what we think this animal was doing was diving and feeding on seagrasses. Here's a reconstruction of the skeleton, and many of the features of the skeleton depart from what we see in other sloths. So it's a sloth, it's sloth-like, but we see an evolutionary lineage as this animal is becoming more and more adapted to swimming and living in an aquatic environment. And one of those features that we see is the bones are becoming thicker and thicker. So if you look at Thalassocnus here, you can see it's becoming very dense bone. It's becoming negative buoyant to allow it to swim down to harvest and feed on the seagrasses. And we actually have remains of the fossil seagrasses in the Pisco Formation. And this becoming pachyostotic shows up in virtually all of the limb bones of this animal. And of course, so what we see is, while it doesn't reduce the hind limbs or using the tail as in dugongs and manatees, the bones are becoming much thicker. In fact, there was previously one record of a manatee from this formation. It was based on a single rib. And of course, now in retrospect and restudy, that rib is from the aquatic sloth. So there were no manatees competing with the sloth for seagrass food. So here is an example of what the sloth would have been feeding on. Here's the fossil. Most of it grows around Australia today, but there's actually a relic population in northern Chile, south of Peru. So we actually have a relic population of the seagrass that we find in the Pisco Formation. So this is our interpretation of what it might have looked like with extensive seagrass beds and with Thalassocnus coming down, possibly using its claws to dig up the mats of the seagrass for feeding, and then basically having a diet. Because based on the geology, the shoreline of South America at this time in the Miocene and Pliocene was just as devoid of vegetation as that initial picture I showed you, where there was no plants whatsoever. And so you basically had this animal moving out, it probably in low tide to shallow water to feed, and eventually becoming more adept at swimming and being able to go deeper for that. So please keep calm and sloth on. Thank you for your patience.
So this webinar is for the International Union of Conservation of Nature, ASASG, Xenarthran Specialist Group. And we have a website, xenarthrans.org. We have lots of information there. And we are also active on Instagram and Facebook. And we have our YouTube channel where we post all of our past webinars, as well as some animated videos, which we're going to talk about in a little bit. If you go to xenarthrans.org, you will see that we have species profiles of all of the extant species. We have their body descriptions, habitat ecology, reproduction strategies, their ranges, and that's really for adults. But now we're getting into some kids material. And Greg, I just added this top left video for you just now during your presentation. So we have 4 animated videos. We have each of the videos in English, Spanish, and Portuguese. We have one on anteaters, one on sloths, one on armadillos, but then we have one on the past, present, and future of Xenarthrans. And we encourage you to utilize our resources. They're all free. We also have worksheets and coloring sheets and spot the differences and crossword puzzles and word searches that accompany those videos, so you can incorporate them into your classrooms. Before the presentation, we were talking about how Greg celebrated International Sloth Day 2 Saturdays ago. And coming up, we have World Anteater Day. Now, Armadillo Day and Anteater Day, they are the same date every year. But the International Sloth Day, that changes every year because it's on a Saturday. So it's the 3rd Saturday of October. So next year it's going to be a different date, but it's always the same part of the month. But many people get confused, so I have to explain it every webinar. We have one more webinar for 2023. It's going to be next Wednesday, and it's going to be about the Upside Down Book of Sloths. But more specifically, it's going to be about how teachers can utilize this book and other nonfiction books into their classroom, because we all know that their science units are getting shorter. So if you're getting a shorter science unit, but you're still having to read to the kids, why don't you do something about nonfiction, or more specifically, Xenarthrans? So the author and the person who created those lessons will be joining us next week. Then we're going to take off December, but we'll be back in January. If you work with Xenarthrans, extinct or alive, please send me photos so I can update our Facebook and our Instagram page. I would love to do that. You can email me at kenny@kennycoogan.com. If you feel inspired to save our extant species, we have a donate button in all 3 languages. And you could just give outright, which we appreciate. But as you notice, I'm wearing a beautiful ground sloth long sleeve. And we have ground sloths, modern day sloths, anteaters. We even have a glyptodon. Greg, you could be getting a glyptodon bag, shirt, hoodie. So if you go to this store, we ship internationally. They ship internationally, and all the proceeds benefit Xenarthran conservation and education initiatives for our specialist group. And who else supports us is FIA, the Foundation for International Aid to Animals, and Nurtured by Nature, who did the last webinar for us. So these two organizations help us put on our monthly webinars and create educational content for you. All right, Greg, I'm gonna now read you some questions. I will try to remember my 7 years of Latin. So Finn asks, when do we think sloths made the transition from land to an arboreal life, since we are missing the modern day fossil record?
Well, right now, it's based on a molecular clock. And so if you kind of look at that first slide that I showed you, if we assume that what we could morphologically consider to be Coleopus or Bradypus, we're probably looking back, maybe 20, 25 million years in that neighborhood. But I mean, once again, that's an estimate based simply on the divergence and the molecular clock. And I should point out that when you look at the genetics, Bradypus doesn't really fit in with all the other sloths, whereas Coleopus, well, originally was put in with the Megalonychids. Recent genetic work has suggested that maybe it's more of a Mylodont. And so there's still some ongoing questions in that. But obviously, we have no idea when the morphological adaptations that makes them permanently arboreal get in. But looking at a lot of the fossil sloths, we see semi-arboreal sloths clear back in the Miocene, where we've got good skeletons. And if you compare them with, say, Tamandua as a semi-arboreal Xenarthran, they look very similar in their adaptations.
And I think Tigger also kind of commented about the suspensorial lifestyle, that it probably, or it did evolve twice for the two different modern day genera.
I agree totally. I think it's a wonderful, wonderful example of parallel evolution, where two different lineages. But as you saw with the rotation of the hind foot, there we saw 4 different lineages that modified their foot. And of course, I don't think that had anything to do with getting into the trees. But we certainly do see in the fossil record that a number of sloths did get into the trees. I'm working with a colleague in Brazil, Mario Dantas, and one of the things we're looking at now is it possible for small juvenile sloths to get into trees, kind of like bears do, and then they get eventually to such a size they no longer can get into trees. So we're looking at changes in body size and modifications of the limb bones in order to be able to climb into trees.
Do we know how fast ground sloths grew?
The biggest challenge we have is that we really have no way of coming up with good yearly ages to put on an animal. We can make estimates of their lifespan for adults, based on relative size. We do have a fossil family group of what we interpreted as a female, a juvenile, and a newborn. And the juvenile is about 1/3 the size of the female. And if our estimate that she gave birth at about 1.5 to 3 year intervals, that would mean that it got about 1/3 of its size in 3 to 4 years.
All right, so Jen asks, for specimens where we have several samples, are there notable morphological differences between males and females? Or how did you know that was a family of a male and a female and a baby?
Okay. I mentioned Paramylodon, and there is a very large number of individuals of Paramylodon from the La Brea tar pits in Los Angeles. So it gives us a good statistical sample. And looking at that sample, we saw differences in the caniniform and the way it wore. We saw differences in some of the morphology of the skull. And so we sort of divided them into males and females, or I should say, we felt we could see there was a difference in sexual dimorphism. Now, obviously, if I'm going to be chauvinistic, I'm going to say, well, the males are big and macho and the females are not so much. But getting back to that family group I was describing before, let's look at it this way. We don't think that sloths were social in terms of the male staying around, so that your basically family group was the female and her offspring. So if you don't have the male there, like in a pride of lions protecting the offspring, that falls on the female. And so it makes sense that the female might be larger than the male. And we see in some of the tree sloths, this is true. So I'm going to argue that the larger, at least the larger individuals of Megalonychids that we have are probably female, and the smaller ones are the males.
All right, so Tiger asks, for the fur, were they porous like modern sloths? And I'm sorry, did you explain those bumps, the purpose of the bumps? Do we know the?
Well, the bumps, the little white things, are bone, and they're dermal armor in the skin. So they're basically, but, in the armadillos, of course, you've got this really nice, well-organized armor where all the individual osteoderms come together and makes a solid shield. Whereas in the sloths, it's kind of a mosaic, and some of them will grow together, but it doesn't form a contiguous armor like you see in armadillos. In the hair, we do not really see structures that could be interpreted as places for algae to grow like we see in tree sloths. But once again, if you're living in Tierra del Fuego, which is a colder and a drier environment, you're not going to have all the available moisture and high relative humidity that tree sloths have that allows the algae to grow in their hair in the tropics.
And all of the giant ground sloth hair is parted on their back, not their stomach?
Yes. It's kind of hard to say, because once again, when you're only dealing with a piece of skin that's out of context, it takes a little bit of extrapolation in terms of that one illustration that they had interpreted seemed to fit where it would be on the body.
All right, Greg, this is, you're going to need to translate this for me. Andreas says, is there any consensus on the relationship between extant and extinct sloths? My understanding was that according to morphological features, Calepus sloths were assigned as close to Megalonychidae.
Megalonychidae, yeah.
But the DELSUC 2019 article about metagenomics shakes up the family tree. So, Greg?
Yeah. Based on morphology, if you look at Coalepus, it has a nice enlarged caniniform in front and simple peg-like teeth, which is what you see in the Megalonychids. And this idea that Coalepus and the Megalonychids were all part one family package was developed by Dave Webb a number of years ago, and had been also talked about by other people previously. And so, yeah, the recent genetic work, which has suggested that maybe Coalepus is a mylodont, is something to investigate. But once again, when you saw that great variety of sloths that we have, we've only got the genetics from 2 or 3 genera. We've got it from Nothrotheriidae, we've got it from Mylodon darwini, and we don't really have it from a megalonychid, an extinct megalonychid. So part of what we need to do to really resolve this is hopefully find some really phenomenally preserved specimens that will give us more DNA sequences and increase our diversity of fossil sloths. Because once again, you're going to match up with whatever you've got, and that doesn't mean you've got a whole lot of alternative choices that might be a better match than what we've got so far.
How does ground sloth diversity compare to, like, what animal would we think of today that's like that diverse?
Oh boy, that's a good one.
Because all these animals lived within the same 1.5 million years, or 1.8 million, or not?
No, I mean, I obviously cherry pick different genera. If I did each genus, we'd be in trouble.
That would be the long version of the
Yeah, that would
PowerPoint.
be the very long version. So you did see the initial family tree I showed where we had the Megatheriidae. And so we can think of those as high browsers. So their ecological niche might be like a giraffe, and sitting upright, using their claws to hook branches, they're going to be bringing it down to feed. When we look at the Nothrotheriidae, we're looking at low browsers. They're small animals, they're feeding close to the ground, and so we know from their dung that they were eating desert plants. And so it's a Nothotheriops is desert adapted and not in the tropics. And then we have the Megalonychidae, which not only have the grabbing teeth in Megalonyx, but triangular slicing teeth in other genera, that they're using that to clip off branches. And they're a browser, but they're browsing differently. And then we've got the Mylodonts, which we're seeing are living in open country, plains, savannas, the pampas, and are feeding on grasses and sedges and low-lying vegetation. So you've got 4 very broad separations within that of browsers and that. So they're kind of what you see in artiodactyls today. If you go to the African savanna and you look at all the various types of antelope, you've got browsers, you've got grazers, you've got open plains, you've got forest animals. So if I had to make sort of a rude comparison, I would say the diversity in sloths in South America and eventually the Caribbean and North America is analogous to the diversification we see of African antelopes.
All right. Andreas would also like to know, was there any signs of inter or intra-specific fighting like we see in the extant sloths?
I have not. I've looked at a lot of fossils and I have not seen anything that I could interpret as indicative of any intraspecific fighting. So, you know, I haven't, if I found 2 that I thought males with locked arms or something like that that fell into a tar pit, maybe I could give an answer to that. But, you know, behavior is really hard to infer from the fossil record. And so it's going to take a really spectacular specimen to give us something like that. It's not, you know, maybe if we found a puncture mark in the sinuses of the skull, or a claw went in or something like that, or the shape of it fit a claw, we might be able to make that inference. Or we might say, well, maybe that came from a saber-toothed cat that was going after it. I just can't give a good answer to that one.
All right, well, in related news, Shane would like to know, you mentioned the possibility of humans hunting ground sloths. What kind of theories do we have about the ground sloth's defenses against other predators?
Well, if you look at a ground sloth's body, they're very pear-shaped. Look at that huge wide pelvis that they have. So the center of gravity in sloths is shifted towards the back part of the animal. And you often see sloths mounted in an upright position. So what's an animal that we know that's a Xenarthran that gets into an upright position to free its claws? Sloths are not going to run away. They're not speedy animals. And that. So for those of you who work with modern anteaters, you're all familiar with the embrace of the oso hormiguero, and that those claws can be very useful. And there are YouTube videos of the giant anteater defending itself against a jaguar. And so I can see first, if a sloth saw a predator coming, what it does, it rears up. Now it looks a lot bigger than it did when it's down on all fours. And it has freed up those claws on the front hand. It's got its tail as sort of a prop. And one of my ad hoc explanations for that weird hind foot, remember how I said it could pivot like this relative to the lower leg? If you're down on all fours, it gives you a little bit more room to pivot your body without having to take steps and be off balance. So I kind of have speculated. It's one of those thought exercises that we do as scientists of what makes this a useful adaptation. And I'm thinking that part of that may have been to make sure the animal had a little bit more ability, not only for swinging at predators, but also maybe just if it's sitting upright and reaching in trees and trying to hook branches for food.
All right. We have a couple more questions. Shane says, thank you. Finn asks, do you agree that giant sloths dug their own burrows as well as used already present caves? And you kind of answered this earlier, but did any of them live in groups or herds?
I think based on what we were seeing in Paramylodon, that they probably may have formed extended family groups. The Megalonychid sloths were probably just the mother and young. So I think there was, once again, if you're going to infer behavior, it wasn't one size fits all. Different ones did it. So the fact that we get so many Paramylodon in the tar pits certainly suggests they were very common in the area. And so there may have been, I'm not talking about wildebeest size herds, but certainly larger family groups in that. In Rampart Cave in the Grand Canyon, we get the one I showed the pictures of with all the dung with Nothrotheriidae. We have the female, and there are skeletons of juveniles also. So we view caves as potential birthing dens, and maybe latrines. There's over 2 meters of sloth dung in Rampart Cave. So you either had one sloth with a very bad case of diarrhea, or you had many, many sloths over thousands of years making contributions and reusing that cave over many generations. So we can keep that in mind as an option as well. The other thing to keep in mind, if we assume that extinct sloths, like modern sloths, have a low basal metabolism, and that's why they still have long hair on them, although it's been postulated that the bigger sloths might have been like elephants and had thinned out their hair. But caves maintain a stable environment in terms of temperature. The temperature of a cave approximates the mean annual temperature for the year. So a sloth can thermoregulate itself in the wintertime going into a cave. It's reducing the difference between its body temperature and the outside temperature where it's cold, and so is going to save energetically by being in that cave. By the same token, if you're in a desert environment like Nothrotheriidae and it's really hot, maybe they were coming out and feeding at night, and during the day we're going into caves because it's going to be relatively cooler and they won't have to worry about overheating. And we find certainly many, many sloths in caves of many different taxa. And some of it may be a taphonomic bias in terms of, like the Caribbean, you've got limestone, you've got lots of caves, and that's where they get preserved. But we also find it's also very true on the continents that it's not uncommon to run into sloths preserved in cave sites.
All right, Greg, I think we got 2 more questions. Andreas asks, do we have evidence of Xenarthrans articulations in extinct sloths, since tree sloths don't have it?
Well, actually, yes, we do. All of the ground sloths do have Xenarthrans articulations, and they're very well developed. And in fact, in some of the ground sloths, you'll actually find another articulation between the spinous processes of the vertebrae where they articulate. So it's not only the normal Xenarthrans condition, but you're also getting another one on the midline. So they're not as well developed as in anteaters or in or armadillos, but they're definitely there in the lumbar vertebrae.
All right, and now we have Mariella live in Mendoza. Her question is it possible that the common ancestor of the Xenarthra had osteoderms? Because why do they all have those bumps?
Well,
she didn't say that. I just added that.
all right. Well, actually, I don't think the osteoderms are a common ancestral trait, because if it was, why don't we get the osteoderms in the Megalonychids, the Nothrotheriides, and the Megatheriidae sloths? They don't show up in the Scelidotheriidae mylodonts, and they don't show up in all the mylodonts, just one particular lineage. So if you plot out characters and you create a family tree, independent of having the osteoderms, you get about 4 or 5 genera that lump together that are closely related based on other characters, and they all have the osteoderms. So I consider the osteoderms in the mylodont sloths as a neomorph and not an ancestral character.
All
Very
right.
cool, thank you. And there was an additional question by Finn, but she sent it via direct message to me. Could they use their teeth as weapons?
Certainly in the Megalonychid sloths with the teeth are self-sharpening and the front caniniforms, I think they could have been used as weapons. And I'm sure that there's people out there who've handled Coelipus and have these scars to show what a sloth can do with their caniniforms. So
Oh, yeah.
yes, I think it's very possible that that could have also been used as a potential means of defense. Good point.
All right, very good. Anything else, Mariella?
I think that's it. That
Andre-
was really awesome. Thank you so much, Greg. It was really interesting and fascinating.
My pleasure. Thank you for the invitation to participate. But